Hi grade 12s, we're on to topic 6.2. This is still a topic under equations, and technically these are still grade 11 examples, but they're the more complex examples from grade 11. So let's have a look. Example 1 says solve for theta, and the question says 2 sine squared plus cos theta minus 1 equals 0. Now the first thing I'm just going to note to myself here is the fact that there's 3 terms. And I'm going to explain that a little bit more when we get to an equation with 2 terms, where there's various options for us. But this is 3 terms. Now, if ever my equation is 3 terms, I don't like to have a mixture. And the reason why I don't like to have a mixture is that I'm clearly going to have to factorize, because I can't isolate one of the trig ratios without factorizing. And a mixture is not helpful. And so if I can avoid having a mixture, I do. Of course, sometimes it's not possible, and we will look at an example like that. So what I need to do is I need to get rid of the mixture. Basically, I want only one trig identity if I can. And the only way to get rid of one of the one of the trig ratios, my apologies. So I want to get only one trig ratio. So the only way to get rid of one of them is to use an identity. So the first thing I look here is the only identities I know. So if I write here a note to myself, the identities, the one identity is that sine squared of an angle plus cos squared of an angle is 1. And we all know that therefore 1 minus cos squared is sine squared, and 1 minus sine squared is cos squared. And the only other identity which we have at the moment, if you think that this is a grade 11 example, the only other identity is that tan theta is sine theta over cos theta. Right, now what here could help me? Well, I don't really want to change cos theta to something with tan theta. We're going to come to tan in a moment. But the moment I see this, I don't look at the cos, I see this sine squared. And I say to myself, can I replace sine squared? And the answer is yes, because sine squared is 1 minus cos squared. Now, of course, you never know if you're doing this correctly. You never know if it's going to work out, but you start, and then you see where you get to. If it doesn't work out well, then you start again. Now, why I think this will work out nicely is that I now only have cos in my equation. Yes, I have cos squared, but that's not a problem. I can just make this a trinomial. So if I write my cos squareds first, then cos theta, and 2 take away 1 is 1. So I've just added my constants. Now, personally, I don't actually want to factorize that with a negative coefficient of cos squared. So if I divide through by a negative, and again, you could use an a instead of cos theta to factorize this using a, but this isn't too difficult. So it's 2 cos theta and cos theta, and it's minus 1 plus 1, I think. So perfect. I get the fact that cos theta is equal to negative a half, or that cos theta is equal to 1. And cos is such a great equation to solve because it's just plus minus. So pick up your calculator, you do shift cos of negative a half, and I get 120 degrees, so it's plus minus 120 degrees, plus k 360, where k can be an integer. Okay, or when is cos theta equal to 1? Well, theta must be equal to plus minus 0. Now plus minus 0 is just 0. So it actually just lands up with kind of like one solution. Great. Now, hopefully if it's a trinomial, the equations you land up with in the end are quite simple, because the difficulty here is this part. It's not the final actually solving. So, most important thing from this is that 3 terms, I generally try and get myself down to 1 trig ratio, so that it generally then becomes a trinomial. Now, let's have a look at some other examples. So question B, again, I see 3 terms, and I see a mixture. So once again, I say to myself, can I get rid of one of these ratios? And I see cos squared. So I'm going to change cos squared to 1 minus sine squared, and hopefully this will become a trinomial that can factorize. If not, then I go back to the drawing board. So if I multiply out, this looks like a fairly standard question similar to question A. It looks like it's going to be a trinomial. So I get negative 3 sine squared theta plus 2 sine theta, and 3 take away 2 is 1. I would definitely divide through by a negative because I don't like factorizing with a negative leading coefficient. And once again, this is fairly easy trinomial. Chances of you having to use the formula in a question like this are so small, because that's quite mean. So I get -1 and I think +1. So I don't know why I wrote cos in that equation, because that's just silly. So if I multiply out, I can check that it's 3 cos squared, and then, 3 sine squared, minus 3 sine theta, plus a sine theta will give me -2 sine theta, and then -1. So that's perfect. So again, you'll end up with two fairly simple equations. So I get sine theta is equal to -1/3, or sine theta equals 1. Now, unfortunately, sine is a little bit more annoying to solve, because you actually have to go find the two solutions. So first of all, don't forget that you do shift sign of negative, you include the negative of -1/3, and I get a value of -19,47 degrees plus K360. And then don't forget that the second answer is 180 minus that. So if you do 180 minus that, I probably wouldn't show that working. I would just go straight to 199,47. So don't forget, it's 180 minus that answer. So it's not too much effort. Then with sine theta being equal to 1, it's funny how 1 always lands up with a weird thing, because theta, if you shift sine of 1, you get 90 degrees. But if you do the second solution and you do 180 minus 90, you still get 90. So you actually only land up with one solution. Now you'll remember from A that that was the same thing that happened in A. So whenever a trig ratio is actually equal to 1, your answers land up coinciding. So you actually only have one answer in the first 360. So A and B, very similar concepts. You notice it was 3 terms, and so getting to one trig ratio is most helpful because it becomes a trinomial. Just don't forget that this answer for a ratio for sine and cos can't exceed 1. So often these trinomials get you an answer for the trig ratio which is bigger than 1 or less than -1, and then you can't continue with that. So they like to ask things like that. Okay, so let's look at C. So this is a little bit more interesting, because I see it's 3 terms and it's a mixture, but it's a little bit of a complicated mixture, because if I change this to 1 minus cos squared, I would then have a mixture of cos squareds and sine and cos and a constant, and that's not going to be a trinomial. And the same thing if I change the cos squared. If I change the cos squared to 1 minus sine squared, then I'm going to have sine squared, I'm going to have a sine theta cos theta term, and I'm going to have a constant, and that's not going to be a trinomial. So this is one of those rare examples where you can't really get rid of the mixture. Whatever you try, the mixture exists in the middle term. So what happens when the mixture exists in the middle term as well? Let's go and make this a little bit easier to handle. So if I make sine theta a, so that will be 2a squared. This will be a. Let's make cos theta b, and this is b squared. Now, let me take out the b's for now. Let's just say this is 2a squared plus a minus 1, because that's a coefficient of 1. So let's ignore the b's. Does that factorize as a trinomial? So this is 2a, this is a, this is plus 1, and this is minus 1. So it absolutely does. So this factorizes. So how could I add in b's so that this is also factorized? Well, if I put a b there and I put a b there, it's equal to that. Now let's just check. That's 2a squared. That's 2ab minus ab is 1ab, and then minus b squared. So actually, now I've factorized to the first line. So this is my first line, this is my second line. So by factorizing the second and then adding in my b's, I've actually factorized the first brown line. Now how does this relate to the question? Well, this is a squared, this is a, b, and this is b squared, which means you actually can factorize this horrible mixture. It is a trinomial, as weird as it looks. So this is actually 2 sine theta minus cos theta, and this is sine theta plus a cos theta. Now I would literally do this all on my question paper, definitely. Probably wouldn't do it on my answer page, because then you have to say let A equal sine, and you could actually do it formally, but I just scribble that on my question paper and then figure it out from there. So this is quite rare. You can't get rid of this mixture because the middle term is also a mixture. And if you can't get rid of a mixture, you need to embrace it. You can't beat them, join them. And in embracing it, I mean treat it like a trinomial. And so this leads me to the next kind of interesting question, which you might not remember from grade 11, which is that 2 sine theta minus cos theta will have to equal 0, or sine theta plus cos theta equals 0. Now this is in a type of example which we're going to do in example 2, and these are both tan equations. And the reason why I know they're tan equations is that they're two terms, and most importantly they involve sine of the same angle and cos of the same angle. So when we write notes in the second example, this is going to be the trigger for me when I see it in an exam. There's two terms, which means it's not a trinomial. There's no common factor or anything, so I can't factorize, and they have sine theta and cos theta. Now when we do example 2, we're going to see a different type of example where it involves sine and cos, but these ones involve sine theta and cos theta, which means to me this is a tan equation. Reason being, if you take over the cos theta to the other side and you now divide both sides by cos theta. Now we always tell you to never divide by a variable in equation because you lose a solution. So why am I not losing a solution here? Because while my cos thetas cancel to 1, you haven't actually destroyed cos theta. You've just put it at the bottom on the other side. So it hasn't cancelled away. You've written it somewhere else. Now why have I done that? Because sine theta over cos theta is tan theta. So I actually get 2 tan thetas 1, which means tan theta is a half. Now tan examples are very easy to do because it's just shift tan and then plus k180. So if I shift tan a half, I get 26,57 degrees plus k180. K is an element of integers. So we will discuss these type of ideas and write a little bit more notes in the next example. On this side, I would say sine theta equals negative cos theta. I would divide by cos theta on both sides, basically so that you're just rearranging to put cos theta at the bottom so that it becomes tan theta. And shift tan of negative 1 is negative 45 degrees plus k 180. K is an element of integers. Okay, so this was diving into two concepts. This is a really, really interesting question, but it's diving into two concepts. Number one, the idea that if you can't get rid of the mixture, embrace it and try and figure it out as a trinomial. And secondly, if you have a sine and cos equation where it's just sine and cos, and it's just two terms, and their sine and cos are the same angle, you can morph it into a tan equation. Now, I haven't quite finished here because this gave a specific domain. It said between negative 360 and 360. So now, I just need to go and find out what angles are actually specific in this particular domain. So 26,57 works. If I add 180 to that, that'll also work, and that's 206,57. If I add another 180, I'll be out of that domain. But if I took that original 26.57 and I minus 180, I got minus 153,43 degrees. If I minus another 180 from that, I actually still remain in the right domain. And so that's minus 333,43 degrees. So as far as I know, there's actually 4 solutions from that 26,57. Then negative 45 degrees from the other example, the other solution also works. If you add 180, you get 135 degrees, that also works. If you add 180 again, that is still within the first 360, so 315. If you take negative 45 and you originally minus 180, you got negative 225. But I can't carry on going because then I lie outside that domain. So just don't forget to give the specific answers that they want. Okay, that was quite a mammoth question, I must say. Very difficult question, because it's also worth so many marks if we were going to give it a mark allocation. Okay, let's look at example 2. Now, example 2 is all about that idea, about the sine and cos equations. So there's two types of sine and cos equations. And the first one is, well, first of all, you always look for two terms for sine and cos equations. And then the first type is it could be a tan example. And how do I know if it's a tan example? If you have sine and cos of the same angle. You have to have the same angle, because if you don't have the same angle, you can't possibly reduce it to a tan. So the first thing I ever do when I see two terms and I see sine and cos, I always check, do I have the same angle? Because if I have the same angle, I have a tan equation. So here, for example, I have sine 3 theta and I have cos 3 theta. They're two terms. They're already on opposite sides, which is great. So if I divide by cos 3 theta on both sides, what I land up is tan 3 theta. And that's why they have to be the same angle. Now that equals 2. So I'm going to shift tan of 2. And fortunately, I don't have to find a second solution, which is very helpful. So shift tan of 2, I get 63,4349 degrees plus 180k, or k 180. K is the limit of integers. And then when I divide by 3, which is why I didn't round it off initially, because your rounding can change, I get 21,14 degrees, and everything divides by 3. So this is now k 60. Great, so that's the easy sine and cos equation. If they're the same angle, look out for the tan. Now, what's the more difficult example? The more difficult examples are where you have sine and cos of different angles. And this is where I'm going to go a little bit more slowly. So if you have sine and cos of different angles. Now, what we want to do is we don't want to have sine equals cos. What we would prefer to have, our aim, is to have a cos of an angle equals cos of an angle. Or if you have sine equals sine. And I'll explain why in a moment. The problem with this particular question in B is, yes, I have cos, but on the other side I have sine. Now, preferably, I like to go for cos, if possible, and I will show you why when we do a sine example. So I prefer to get cos equal to cos, which means that this right-hand side has to be rewritten to use cos. So if this is theta minus 20 degrees and I'm happy with that, how can I rewrite sine of 2 theta as cos of something? Well, I would use reduction. So basically I'm kind of anti-reducing, I'm going backwards. Sine of 2 theta would come from cos of 90 minus 2 theta, because you're working from 90, so cos would change to sine, but it would be positive because this is quadrant 1. Now, why is this good for me? Well, let me just make an example below here. If you have cos of 30 degrees equals cos of theta, surely I can logically assume that cos of 30 equals cos of 30. So theta could equal 30 degrees, because then cos of 30 would equal cos of 30, and that is always true. Or would you also agree that when you find a solution for a cos equation, it's always plus minus? So positive 30 degrees has the same cos ratio as negative 30 degrees, because in cos equations, plus or minus an angle gives you the same cos ratio. So when we have cos 30 equals cos theta, yes, obviously theta could be 30, but theta could also be negative 30. That will give you the same ratio. So how does that affect this? Well, how it affects this is that basically theta minus 20 degrees could just equal 90 degrees minus 2 theta. Or theta minus 20 degrees could equal the negative version of 90 degrees minus 2 theta. So that's exactly what I'm arguing here. if cos of 30 equals cos of theta, theta could equal 30 or theta could equal negative 30. So I've made that exact same argument here. Either these two angles are equal or the one equals the negative version of the other. Now the moment you write down a solution, you have to write down the K360. K is an element of integers. So in both of these, I have to write down plus K360. K is an element of integers. Now, I always write down those solutions first before solving. Because if you solve for theta, then you think that the negative version of that theta is also the answer. So try and set up both of these equations before you now go solve for theta. So if I'm going to solve for theta in this first one, I'm going to say, right, 3 theta equals 110 degrees plus K360. K is the element of integers. And then I would divide by 3. So I'll get theta equals 36,67 degrees. But if I divide by 3, I must divide the period by 3. So it's K120. And in the second one, a little bit more complicated because I need to distribute my negative. So it's minus 90 degrees plus 2 theta. So if I minus 2 theta on both sides and add 20 to both sides, I get that. And then I basically just need to divide by my negative. So I get theta equals 70 degrees. Now technically if you divide by negative, that should now be minus K360. But the reality is it doesn't matter because that K is an integer. So it can be positive or negative. And so actually I land up with solutions which actually have different kind of periods to them, in that this is plus K120 and this is still K360. Now I'm just going to write a note here on this because I think this is probably the toughest type of equation. I really think it's difficult. So the point is, if you have cos of an angle equals sine of an angle and they're not the same, then my aim is to get them to the same ratio. So I would prefer myself to get cos of this angle equals cos of that angle. And how we do this is we do reduction. And it's almost like we undo reduction because we do 90 minus our angle. Reason being, what can we do from there? Well, then option number 1 is that the two angles are directly equal to each other and you can solve. Or option number 2 is that the one angle is equal to the negative version of the other angle. So these two are either equal to each other or the one is equal to the negative version of the other. And then you solve. Very strange concept and definitely ones that need quite a bit of practice. Now, let us do exactly that. Let's practice one and then let's make sure that we try one where we use sine equals sine, just in case they give you that type of example. So let's just start with the cos equals cos again. First of all, what I would notice is that those angles are different. And because the angles are different, this is most definitely not a tan example. So that's my first kind of observation. So this is not a tan example, which means I'm going to change this to sine equals cos because I want them to be equal to each other. Now I'm going to change this to a cos equals cos because I prefer that, which means I'm going to change this to cos, and this will be 90 minus theta plus 30. So it makes that angle messy, but it's not really a problem. Now once you have cos equals cos, it's actually not that bad. So basically 90 minus theta plus 30, so the first angle, could equal 3 theta plus K360. K is an element of integers. Or our second solution is that this 90 minus theta plus 30 could equal the negative version, so it could be negative 3 theta plus K360. And from now on, it's basically just solving an equation. So if I go back up, this is 90 minus theta minus 30 equals 3 theta. And I must say, you do get tired of writing this K360 every time, but it is important. So now if I probably would bring my 4 theta to this side, but anyway, I'll bring my I'll bring my 3 theta to the left, and 90 minus 30 is 60, so if I take it over, it's negative 60. And then finally, I would divide by negative 4. And if I divide by negative 4, I get 15 degrees, but it means I must divide everything by negative 4, so I suppose technically this should be a minus, but it doesn't matter, and this is now 90 degrees. So that's my first solution. My second solution is 90 minus theta minus 30, but this is now negative 3 theta. So I'm going to add 3 theta to both sides. So I'm actually going to get 2 theta equals negative 60, and then I'll divide by 2. And so I get theta equals negative 30 plus, and this is now k, 180 degrees. So once you've done the initial stuff, you're actually just solving a linear equation. Now just be careful, in this example they said, please find me thetas between negative 180 and 180. So now I've got to go, so let's take first solution. So first solution, so they said what, negative 180 to 180, absolutely. Okay, so my first solution was 15, which works. Now if I add 90, I'll get 105, which works. If I add another 90, I get 195, which doesn't work. So let me try minusing 90. So 15 take away 90 is minus 75. If I take away another 90, that's at minus 165, which works. But if I take away another 90, it doesn't. So that's the first solution looked at. My second solution is that negative 30 works. Now I'm allowed to add 180. So if I add 180, I get 150. Now I can't keep on adding 180 because I'll be outside my domain. And even if I take negative 30 and I subtract 180, I'll be outside my domain. So there's actually 6 solutions. So the last thing we need to actually do is let's look at an example. We've forced everything to be cos equals cos because it's a little bit easier. What happens if they give you a sine equals sine example? Now, I always would try and avoid this, but if they give me sine equals sine, I'm not going to change them both to coses because then I'm making my life a little bit more difficult. So, what are my 2 solutions for sine? Well, let me just write myself a note here on the side. If you had sine theta equals sine 30, your first solution would be that theta could equal 30, which it could. Your second solution is that, how do I find the second solution in sine? You do 180 minus. So it would be 180 minus 30, which would be 150. So sine of 30 is the same thing as sine 150. So let's use that same concept here. So first of all, I could say my 2 angles are equal. And then I just have to say plus k360, k is an element of integers, and then I just solve that. So that's one of the ways to do it. However, our second solution, so or this theta plus 10 could equal, and I used to say 180 minus 30, so it's 180 minus this angle of 2 theta minus 50 plus k360. And once you've done that initial writing out, basically you're just solving a linear equation now. So if I bring my 2 theta over, I actually get negative theta equals negative 60 plus k360. And then basically I divide by negative. So I get 60 degrees. So yes, positive 60. So that wasn't too bad. And the next one, a little bit more tricky, because you have to do some multiplying out, some distribution. So 180 minus 2 theta plus 50 plus k360. So I'd add 2 theta to both sides, so I get 3 theta. 180 plus 50 is 230. Take away 10 is now 220 degrees, I hope, plus k360. And finally I divide by 3. So 220 divided by 3 is equal to 73.33 degrees. And this is now plus k120. So I don't think it's actually that much more difficult than cos. It's just instead of doing the minus version, you do 180 minus. Right. Right, and those, I think these two examples are the most difficult ones that you did in grade 11. So the idea of when you have three terms, probably going to be a trinomial. So your first aim was to try and get the trinomial into one trig ratio only. If you're desperate, you can do the mixture, and then you factorize it using the mixture. And then example 2 was about the two types of equations when you have sine and cos. If you have the same angle, it's going to probably be a tan equation. If you have a different angle, you need to try and go for this either cos equals sine, cos equals cos, or sine equals sine, depending on what you prefer really. Cool, well done. Keep going.